Okay, in this video I'd like to try and introduce you to what do we mean by kernel and range. So let's start with a linear transformation from one vector space to another. The set of vectors in V in the starting vector space that get sent to the zero vector in the ending vector space is called the kernel. So let's just look at a really simplistic idea here. Suppose we had a bunch of vectors in a starting set V, and we find what does T do to them. Now this is overly simplified because I'm looking at finitely many vectors going to finitely many vectors, whereas when we're talking about linear transformations in vector spaces, they're infinitely many because we also have multiples of every vector. But just as a way of getting the point across, my kernel would be all things in the starting set that get sent to zero. So which things get sent to zero? Those two things. This would be our kernel. So your kernel is going to be living inside of V. It's actually going to be a subspace of V. Let's write the kernel in a slightly different way, or a formulaic way. It's the set of all vectors V in big V, where T of V is equal to the zero vector. And that reminds me of something else I should mention. Keep in mind that a zero vector in V might look very different from a zero vector in W. In the last video we saw you might have a transformation from P1 where the zero vector is really going to be 0x plus 0 into M22, where the zero vector in 2x2 matrices is going to be 0, 0, 0, 0. So keep in mind that your zero vectors are going to look a little different depending on the space. But the kernel is which things get sent to the zero vector. Okay, the range is just what you would expect the range to be. It's a set of all images, the set of all vectors in the ending space that are T of something in the starting space. So if I tweak my example very slightly, my range would be not everything in W because it doesn't appear that anything goes to Y3. So my range would actually be a subspace of W. Again, this illustration is not the greatest illustration because it's assuming there's finitely many vectors, but I guess if we included multiples of them, maybe this would be okay. Okay, let's look at an example. Let's start with a nice simple one. We've seen before the function which represents the derivative. So the derivative of ax squared plus bx plus c is equal to 2ax plus b. Okay, so our vector space V is polynomials of degree 2 or less. Our vector space W is polynomials of degree 1 or less. Okay, so let's think about what does the zero vector look like in W. It looks like 0x plus 0, or the zero function. So if I want to find the kernel of this transformation, the kernel of D, it's a set of all vectors in the starting space. It's a set of all things that look like ax squared plus bx plus c in the starting space, P2, where T of that, in this case D, is equal to the zero vector. But we've seen some calculus maybe once before in our life. We know when the derivative of this is going to be 0, what functions have their derivative as 0, when is 2ax plus b going to be equal to 0? Well, when a is 0 and b is 0, which means that c could be anything. So the kernel is actually going to be the set of all things where a is 0, b is 0, and c is anything. So an easier way to write this would be the set of all constants. set of all constants is the kernel of differentiation when we're talking about derivatives of polynomials. Those are the things that their derivatives end up being 0. Okay, if I want to find the range, I should have also written down the symbols for the range. Let's maybe go back and do that now. The range of a transformation T can be written as all vectors W in W such that W is T of V for some V. Okay, that's a mouthful. There's probably easier ways to write it. Let's see if we can figure it out for our function right here. Let's try and find the range of differentiation. So it's a set of all vectors W such that W is equal to T of V. An easier way to write that would be it's a set of all T of V's where V is coming from capital V. So it's a set of all outputs given any input. And so if we think about it this way, the range of D, this particular D, is going to be the set of all outputs. T of V would look like 2ax plus b, where v is in V, meaning ax squared plus bx plus c is in the vector space V. And actually, if we compare this to our set P1 or set W, it seems like everything in P1 is going to be of this form, because this is really the span of x and 1. Everything that's in this set is going to be a multiple of x plus a multiple of 1. So it's a linear combination of x and 1. It should be in the span of x and 1. So we can write the kernel as just multiples of the number 1, just single constants. We can write the range as x's and 1's.